Definition definition of average speed: total distance over total time. Average speed, which is different from average velocity. Average velocity is equal to final position minus initial position over whatever time interval you are considering. So you have two different situations, one and another. The total distance is 6 kilometers plus 6 kilometers. Now we have to find what is the total time. So what is the total time? The first segment, x, is equal vt, has no acceleration, x 6 kilometers. Speed 50 kilometers per hour, which means you can determine the time in the first segment, 6 kilometers divided by 50 kilometers per hour, and you have the time in hours. And then you do the same for the second segment. It's going to be 6 kilometers divided by 9 kilometers per hour. So when you sum these two times, you can plug it in here. The total distance, you can plug it in there, and then you have your average speed. Suppose that a car traveling to the west begins, so it's always good as you read anything, you do a little diagram, east, west. Excuse me. Suppose that a car is traveling to the west, begins to slow down as it approaches a traffic light. So it's going to west and it starts to slow down. So you could represent by something like this, right? If you take a picture of that motion at equal time intervals, you have something like that. Okay? Which of the following statements about its acceleration is concerned? Remember, if you have a slowing down situation, slowing down, velocity, and acceleration have different directions. The vectors that indicate velocity and acceleration oppose one another. So in this case, our velocity vector is towards west, is a westward direction. So if it's slowing down, the acceleration vector must be opposing, or must be set in the opposite direction. If you had set your west to the right, the velocity vector would be in that direction, and acceleration would be the other one. So this is not a good answer. This is a good answer. A rocket from a volcanic eruption is launched straight up into the air with no air resistance. Which one of the following statements about this rock, why it is in the air, is correct? So this, if there is no air resistance, so we are talking about a free fall situation. And then we always set our zero on the bottom part. Our y-axis is set in such a way that upward Motions are always positive. In a free fall situation, as we saw in class yesterday, acceleration is always pointing downward, and and therefore we'll have a negative sign, right? Negative sign. The reason is it's pointing downward. So let's say on the way up, its acceleration is downward and its velocity is upward. And at the highest point, both its velocity and acceleration are zero. Well, the velocity is zero at that point, but acceleration is always, no matter what happens. So go all the way up and then momentarily stop and falls back. Velocity is zero here, but the acceleration is not. On the way down, both its velocity and acceleration are downward. That's good. And at the highest point, both, no, throughout the motion, the acceleration is downward and the velocity is always in the same direction. No, because it's as it comes down, the velocity change direction, the acceleration is downward at all points of the motion. This looks good. The acceleration is downward at all points in the motion. No. A 10 kilograms rock, a 10 kilograms rock and a 20 kilograms rock are dropped from the same height and experience no significant air resistance. Again, free fall situation, there is no drag forces impeding the motion. Acceleration is negative 9.8 or negative g. If it takes 20 kilograms rock time t to reach the ground, what time you take the 10 kilograms? Oh, it's the same one. It's no problem. Time is the same. What is this? The motions of a car and a truck along a straight road are represented by the velocity time graphics in the figure. The two vehicles are initially alongside each other, time equals zero. So this is velocity and time. Please read the graphic so you know what it is. It's not a graphic of position versus time, it's velocity. The slope of a velocity versus time gives what? Acceleration. So for the truck, as you can see here, the acceleration of truck is zero. Right? So if there is no rise, the acceleration or the tangent as being rise over run, there is no rise here. So acceleration is zero. Whereas the car has an acceleration that is positive, right? So the rise is given over the run gives some value. I don't know which one. Acceleration, whatever. Okay. At time t, what is true of the distance traveled by the vehicle since time t equals zero? So both of them, supposedly, at time equals zero, they were the same point. Car and truck. Oops. Right, truck. All right. So the truck at time equals zero has some velocity already. So it's kind of a, you know, moving with some speed. Let's say 40 miles per hour. The car is not, right? And the car keeps speeding up, as you can see here. And then eventually the car will match the speed of the truck, and then it's gonna be it's gonna have a speed bigger than or larger than the truck. But if you consider the track, the distance the track travel is equal to its speed, right? V, whatever that is, times the time t. which is this time over here. Now, whereas for the car, the distance the car traveled is equal to, since you have an acceleration, remember our equations of motion for a situation in which acceleration is given, the displacement is equal to initial velocity, so the car was not moving, times t plus half a t squared. And in this case, the acceleration, how can you take the acceleration, is the slope of velocity versus time. So what is the slope here? The slope is the rise over run. So acceleration is the rise v over run t, v over t. So when we plug it in here, since initial position is 0, x for the car is equal half acceleration v over t times t squared. So the car motion or displacement of the car is half vt. So it's less than a truck. So if you also consider that the area over the curve, velocity versus time, gives you displacement. So if you take the area for the truck, you can readily get your VT. And if you look at the area velocity over time for the truck, for the car, you have the area of a triangle, half the base t over the height, which is v. So this is the right answer. The area under a curve in a velocity versus time gives you displacement. Oh, we just saw that. Very good. A runner run the marathon approximately 42 kilometers in this much time and this much time. What was the average speed of the runner? So what is the definition of average speed? We just saw in the beginning. Average speed is equal total distance divided by total time. So what is the total distance? 42 kilometers. What is the total time? 2 hours and 57 minutes. So now you have to convert these to some decent units, right? So you see that all possible answers are given in meters per second. So we have to make conversions. So 42 kilometers is equal 42 kilometers, but we want to get rid of kilometers. But we know that if you divide by some quantity by another quantity, you must multiply it by some equivalent so that you don't change the value of it. So this is pretty much 42, 1, 2, 3 meters. And how about the time, which is 2 hours and 57 minutes? So how do we do that? So 57 minutes is equal 57 over 60. Or let's just do one thing here. 1 minute is equal 60 seconds, right? And 57 minutes is equal 57 over 60 seconds. So I was going to convert this to hours, so sorry about that. So we have that much seconds, and 1 hour is equal to 60 minutes. and that is equal to 60 times 60 seconds. So 2 hours and 57 minutes is equal to 2 times 60 times 60 plus this much um, this much in seconds, right? All of these in seconds. And now we need to do that in calculation. Uh, right there. The, so then we have 3.95 meters per second. Oh, there you go. Okay. So it's a tedious work of conversion. So you are driving home on a weekend from school, then it starts to snow and it slow down. You arrive home after driving. How far is your hometown from school? So let's do some diagram here. So let's place my origin and we are going home, right? So you are driving that direction. So you're driving home on a weekend from school and you're going 55. So we want to find this entire distance, right? We want to find the whole thing. So what we know is that the total time is 4 hours and 15 minutes. So it's since we have units of miles per hour and we have answers given in miles, so perhaps would be good to convert 15 minutes in hours. So we would have a fraction of hours on that. So how do we do that? So 15. Let's put this conversion here. 15 minutes. 15 minutes. We wanted that. We have minutes here, right? Minutes. But we wanted that in hours. So, but see if we multiply this by an hour, we have to divide it by the equivalent in minutes. 1 hour has 60 minutes. And we can get rid of minutes, right? So 50 minutes is 50 over 60 of an hour. Therefore, 4 hours and 50 minutes, 4 hours and 50 minutes is 4 plus 50, 15 over 60 of that hour, right? So this is 4 plus 0.4 of an hour. So, well, what am I doing? 15 over 60, this is 4. 1 over 4 is, oh no, I'm messing up here. Sorry about that. Let me see if I have a eraser. Yeah, I do. 1 over 4 is 1 over 25. That is 4.25 of the hour. So we have the total time, and we know we want to find the total distance. So it is given some mileage of the first segment, but we don't have of the other one. Okay, so how can we disentangle that information? Well, we need to find if this is x naught 110 miles. How can we find x1, right? The remaining part, and x is equal x naught, it's 110 miles, plus x1. So in x naught, it is traveled over time t naught, and x1 is traveled over time t1. And then we know that t is equal to t naught plus t1. So you might know where I'm going with this, right? So look at this. There is no acceleration in this type of problem because there is no indication there is acceleration anywhere, and it's talking about average quantities, right? So for the first segment, we can say that x naught is equal v at that segment versus the time. Okay, then we can determine the initial time before it starts snowing, and that is equal to 110 miles divided by the speed, or the average speed, 55 miles per hour. So we get that. Since we have this time and we have the total time, we can find T1. So T1, the time of the second segment when was snowing, is equal to 4.25 hours minus 1 over 10 divided by 55, which is 2, right? This is 2. I can put 2. 2 hours, which is 2.25 hours. Okay? So now we have time t1, and since the speed that was traveled during that segment is given, we can find x1. So x1 is equal the speed, 35 miles per hour, times the time, 2.25 hours. And then we can get that. So x1 is going to be equal to 35 times 2.25, right? 78.75 miles, and then you can find the total distance, and that is x total is 110 plus 78.8 is 188 miles. Yeah, 190 approximately. Okay, so I put some problems here. If you have trouble solving any of it, just let me know. I'm gonna pass them and see if there is one. Okay, so let's do a problem with acceleration. Is also a motion in one direction, but has acceleration in it. So a jet plane is launched from a catapult on an aircraft carrier. So let's write the given information that are given. Uh, Time, so we are talking about 2 seconds. It reached a speed of 42 meters per second, and assuming acceleration is constant, how far did it travel during those 2 seconds? So what is our equations of motion in case there is acceleration and the acceleration is constant? The displacement, so how much it traveled, is equal to initial velocity versus time plus half at squared, right? So um, so we want to find this. We want to find x minus x naught. We want to find that is equal to initial velocity 0 half times but we don't have acceleration, so we are we are in big trouble. We don't have acceleration, but this information here is given, right? The initial velocity 0, as as I was told, uh, but there is no acceleration. But we have v is equal v naught plus at, and in other words, acceleration in this case, since v naught is 0, is equal to v over t. And then when we plug it in there, is half over v over t squared, and that's going to be half of 42 times 2, and that is 42 meters. Oh, look at this. Air, no air resistance. Again, we are talking about a free fall type of motion. Every time you face a problem and you identified as a free fall type of motion, there are a few things you should always keep in mind. We always consider the vertical upward direction positive. Acceleration is always downward and therefore comes with a negative sign. And if we are talking about planet Earth, it has a value of 9.81 meters per square second. Now, the motion is such that if it is throwing upward, at the highest point, velocity is 0, okay? And then start to come down, but at this point, the velocity is 0, although it has acceleration. Don't forget that, okay? Okay, so a stone is thrown upward with an initial velocity 7 meters per second. So if it's throwing upward, the initial velocity v naught, so it was throwing from here, right? So the initial velocity has a vector that points in the same direction as that of your axis, the same direction that you're assuming positive, which means your v naught, when you plug in an equation, is going to be a positive number, 7 meters per second. It takes, and the velocity, what is the velocity of the stone after these many seconds. What is the velocity of it? That's what you want to solve for. That's what you want to solve for. Okay. What are the equations of motion in this case? V is equal V naught plus AT. That's what we got. And we want to find V, right? Is equal V naught plus AT. The acceleration is negative 9.8 times 0.5. So basically your velocity is 7 meters per second minus 4.9 meters per second. And then you do your calculation. Okay, that's gonna be 2.1 meters per second. What is this? An astronaut in a strange new planet. Oh, a strange new planet. So in a strange new planet, do not take acceleration as being 9.8, and right? So the acceleration in the strange planets is still going to be negative, but not 9.8. This is a specific value for Earth. So an astronaut on strange new planet having no atmosphere, so no air resistance, jumped from the floor is positive 66 meters per second. What is the magnitude of the acceleration? So what is the magnitude? So you want a positive number there, so let's see it. So y minus I naught. So the maximum height is given, right? That's her displacement is equal to V naught t minus half. Instead of writing your g, you write a t squared, right? But again, this equation allow us to find t and a, but you can't solve with two equations, one equation, two unknowns. So so in this case, going back to the problem, I have one equation. If I had used the equation of displacement versus time, I would find myself with a problem. I don't know how long it takes to go all the way up, and I don't have acceleration. My second equation of motion is V is equal V naught plus AT, or in this case, minus AT, right? Minus AT. So I have A naught, I don't have A, I don't have T. So I can't figure this out. So it's always good to go to our third option, and that's Bernoulli, right? V squared is equal V naught squared minus 2A times the displacement final minus initial position. So Bernoulli equation in this situation is good because why? Well, I don't have the time in it. In fact, this equation can be determined if you take the time from here and plug it in this equation. Okay. So and not only that, I know that at the highest point, the velocity at the highest point, Vmax, the velocity at the highest point is what? 0. Keep that always in mind. 0 is equal the initial velocity square, 6.02 square, minus 2 times acceleration times the displacement. And then we can find the acceleration that way. A test rocket at ground level is fired straight up from rest with a net upward acceleration. Okay, so here's a situation. You have a rocket that is launched upward from rest, so initial velocity is zero. So given information, initial velocity of this rocket when it's launched is 0 meters per second and has a upward acceleration that is 20 meters per square second. And this goes on for a time of 4.0 seconds. And the motor turns off, but the rocks continue to coast upward with insignificant air resistance. So this is the first part of what happens. So the rocket is propelled with an acceleration up to a certain point, and then just keep on moving upward with insignificant air resistance. What is the maximum elevation? So the rocket gets to this point, keep on going, and then falls back. So what is the tricky part of this problem? Is this a free fall type of motion problem? Not completely. The first segment is not a free fall because the acceleration is not a free fall acceleration. It's being propelled by, by the rocket itself. And after it reaches some level, then it's a free fall. This segment is a free fall type of motion, but not this one. So in the free fall type of motion, what do we know? We know the velocity in here, because in fact I'm going to call this V1 instead of V0. Take that off. Call the velocity at this point V1. This is 0 velocity, and here is V1. Does that make sense? So I can use the laws of motion here, and then use the laws of motion free fall here. And we can then determine the maximum elevation. Okay. So what is the maximum elevation? Is equal to y0 plus y1. How do we find y0? Well, go down here. I need y0 is equal to v0t plus half a t squared. And then we have y0 is equal 16 meters. Okay. And then it keeps, what is the velocity that reach at that point? Well, the velocity, which is v1, is equal v0 plus at. So v1 is equal to, oh, I'm sorry, the velocity is 20. 20. It's not 2, it's 20. So 10 times 60, 160 meters, sorry, 160 meters. Okay, so the velocity is going to be 2 times the time, 4, 20 times 4, So V1 is equal 80 meters per second. Okay. So now we can go to the second segment. In the second segment, the initial velocity of the rocket in the second segment is the same, 80 meters per second. And we know the velocity at the highest point is 0, right? So we can, in this case, since time is not given, we can use Bernoulli to figure y1. How do we do that? Well, um, v final square, which we know is 0, is equal the initial velocity square, which we just calculated here, plus 2 times acceleration. We are in free fall, remember? Times the displacement, which is y1. And then we can find y1. So y1 is equal 6400 divided by 2 times 9.8 meters. And then we can solve the problem. Okay, so that would be I don't know. So you do the calculation. This is almost 10, this is 20, this is going to be close to 320 plus 160 is 480. Yeah, somewhere there. Okay, so I hope these problems can help you to play around, try to do them all, and then we go from there.